The title of section 4.2 is Kernels and Images. We continue working with linear transformations. So T will always denote a linear transformation from vector space U into a vector space V. This is also true in general for mappings, these definitions that I will cover, but we only need these definitions actually for linear transformations. Here U is called the domain of T. Let me remind you that in undergraduate studies many times we had to figure out the domain of a function given by a formula, and in some cases it was not trivial. We might have had to spend time with it in college algebra or pre-calculus or calculus 1. So the good news is that the whole space U is the domain. We don't have to worry about figuring out the domain. V is called the codomain of T. T can be into or onto the image of T, or also called the range of T, denoted by im of T, or range of T is the set of all vectors V from the vector space V, such that there exists U vector in U for which the value of T at U is exactly V. So the picture is that we have this U vector space and another vector space V. T goes in between them. Every element of U can be used for the transformation because the whole U is a domain, but V is not always the whole image. So many times what we have is that only a subset of V has this property that it's the value of T at some U vector element. In fact, we have a theorem that you have to prove as a homework assignment that says that the image of T is a subspace of V. So for example, it could be the whole V or maybe a proper subspace. If the image of the transformation equals to the whole codomain, then we call T surjective or onto. So in this case the picture is that the image covers the whole vector space V. If it's not surjective, if it's not onto, then we just call it into. If T is not onto, we call it into V. Or we simply say that this is not surjective. Next definition, the null space of the transformation, it's also called the kernel of T, is denoted by null T or ker of T, and it's the set of all elements in U such that Tu equals to the 0 vector which is in V. And this is then another homework assignment to show that the null space is actually a subspace of U. Again, it could be a proper subspace or it could be the whole vector space. Now these proofs can be found in many different places, in many different textbooks. You are welcome to look it up. The important thing is that you should know how to write it down and you should practice it. It is very simple actually, the proof. For example, the null space part was even assigned as a homework for a special transformation which was simply a matrix multiplication as part of a previous homework assignment. Sometimes we also have to, or useful to use the so-called pre-image concept. Pre-image of a set S in the codomain. Sometimes it's denoted with this inverse notation, even without defining what the inverse is. So right now let's just agree that this is a formal notation without mentioning inverse. So this is the set of elements in a set of vectors in U such that T of x is in S. In fact, the inverse doesn't have to exists. So this is not exactly the inverse, but it's related to that. So the picture would be for a transformation T going from U to V is that if you have a subset S, then you want to check all the entries in U that go into that set. And it doesn't have to be a unique going back, so the inverse doesn't have to exist to collect together all the elements in U that map into S. Another definition, T is injective or one-to-one if for all U1, U2 elements in U, if U1 is different from U2, then it implies that TU1, the image of U1, is different from the image of U2. So what this says is that different vectors have different image under the transformation. And this can be stated in a different way. This is called contrapositive. It's not the negation of the statement because it means the same thing, that injective or one-to-one. It says that if TU1 equals TU2, the only way for this to be possible is if U1 equals U2. So this is the contrapositive statement. So with other words, the only way that you have the same image of U1 and U2 is if you started from the same vector. Lemma 4.2.1 is a very important lemma in this section. It says that let T be a linear transformation between vector spaces U and V. Then T is injective if and only if the null space of T equals to the zero vector. So this lemma says that it's quite simple to check injectivity. We have to check the null space. The proof for linear transformations, we always have that T0 equals 0. This comes out, for example, from scalar multiplication property of a linear transformation with the scalar 0. If T is injective, then the 0 cannot have a different pre-image. So only 0 will go to 0. No other vector U different from 0 can have Tu equals 0. Since the injectivity means it also holds for the 0 vector, that only 0 can go to 0 and no other vector. That means only 0 is in the null space. So the null space equals to the 0 vector. So this proves one direction, that if T is injective, then the null space is the 0 vector set. Now let's try the other direction. That means we assume the null space of T equals to the set of 0 vector. And then we suppose that we have two vectors U1 and U2 going to the same place under T. That means the image of U1, TU1, is the same as the image of U2, TU2. So suppose this is true for some vectors U1, U2 from the vector space U. So we use the linearity of the transformation T, and what we do is we subtract the two vectors from each other. Well, in general, we know how to subtract vectors, but let me remind you that the original definition of the difference is that we add -1 scalar times another vector. Well, in any case, then what we have is that this is TU1 minus TU2, since linearity means that we can apply the transformation term by term. And if the two values are the same, that means this is the 0 vector. So that means comparing this first part to the second is that U1 minus U2 vector is in the null space, but the null space is only the 0 vector and nothing else. So that means u1 minus u2 equals to the 0 vector, and then from here we can rearrange this equation and we get that u1 equals the u2. And as I also formulated the injectivity, so if two values are the same, that means we started from the same place. This is one form of stating injectivity. So that means T is injective. So with this we proved both directions, implication, and that means we have the if and only if statement finished. We had a homework assignment already about the dimension of vector spaces. This next theorem specifies more details about the dimension. This is theorem 4.2.2. So mostly we work with finite dimensional vector spaces. If U is finite dimensional and we have a linear transformation T mapping from U into V, or maybe onto V, then the image of the transformation is finite dimensional. And we also have a formula that says the dimension of U equals to the dimension of the null space of the transformation plus the dimension of the image of the transformation. So the proof of this is very useful. In fact, we will need this to solve some of the homework assignments. So let me first, before proving it actually, try to visualize it, what it means to have this kind of arithmetic. So U is a finite dimensional vector space. It has some dimension. The null space is in U, so that's a subspace. Let me denote it this way. So let's say that this is the null space of T in U, and that means that all these points from this null space all go to 0, as the definition of null space goes. And then the whole vector space U has an image in V, maybe not the whole vector space, it could be just a subspace. So here is the image of T. And what the theorem says is that the whole U dimension can be put together using the null space and then adding the dimension somehow of the image. So kind of clear that this additional part outside the null space is related to the rest of the image that doesn't go to 0. And yes, of course, by definition, outside the vectors of the null space all go to some non-zero vector. The proof goes by using basis. We start with the basis U1, let's say UK, basis of the null space. We already had that every finite dimensional vector space has a basis, and the null space is a subspace of U. That means it's a vector space on its own, so it must have a basis. This is in null space. What we do is now we extend it to a basis of the whole vector space U. And we did have a process also before. We just kept adding vectors to an independent list until the span became the whole vector space. So with this process that we covered before, adding more and more vectors while keeping independence, eventually, let's say after adding R, W vectors, we get a basis. So these are the additional vectors. Right now, using our notation, what we have is that the dimension of the null space of T is K. Then the dimension of the whole U space is K plus R. We have this already, that the dimension of the U vector space is the dimension of the null space of T plus R. So the only question is this R the dimension of the image? If it is, then we are done. Here the W vectors are in U, so we cannot use them to serve as basis in the image because it's in a different vector space. So what we have here in the proof, W1, WR vectors. But instead of using those as basis, what we will show that their image, TW1, TWR, this is a basis in the image of the T transformation. So for that, what we do is that we say that for all V vector in the image of T, according to the definition of the image, there is a U vector in the vector space U, such that V equals to T of U. That's simply the definition of the image. Then since U is in the vector space U, where we have a basis, we can write this as a linear combination of basis vectors. So that would be the, for example, using the U1 or U's from 1 to K, and then using the W's from 1 to R, since these are basis vectors. Then if you check what V is in form of the image of U, and we substitute this representation of U with the basis elements, then since T is linear, we can apply it term by term, and we can factor out the constant multipliers. Then the UI's were from the null space, so that means that all this part is 0 vector. And then what we obtained is that all vector in the image can be written as a linear combination of the TWI vectors. All V in the image of T can be written as linear combination TW1, TWR. That means these vectors span the image. We want to show basis property, although this is already showing that the dimension of the image is less than or equal to R. So the question is, are they linearly independent or not? Independent or dependent, these vectors. If they are linearly independent and they span the image, then that means this list is a basis. So to show that they are actually linearly independent, we use this classical step that we used before, that assume that we have a linear combination that gives the 0 vector for some coefficients from the scalar field F. Then we actually can go backward with the linearity and take in the summation and also the scalar multiplication inside the T transformation. So right now we are applying the linearity property backward. But then what we have is that according to the definition of the null space, this linear combination is in the null space that had basis U1, UK vectors. So then that means that this sum, since it's in the null space, can be written as a linear combination of the basis elements of the null space, for example with coefficients di. But then rearranging this to have everything on one side and equaling it to 0, we get that the only way for this to happen is if all the coefficients are 0, because there are basis elements actually in the whole U space. So what we have is that all the i's and ci's should be 0, and that means that the only way to get 0 from a linear combination of TWI is using the trivial linear combination. So only the trivial linear combination of TW1, TWR results in 0 vector. And we have that in this case, this is a linearly independent list. And since we already had that this also spans the image, it's also a basis of the image. If this is a basis of the image, we get that the dimension of the image of T is R. And with this, we obtained what the theorem said. We also have that this is finite dimensional, and that the dimension of the U vector space that we wrote before as K plus R is actually the dimension of the null space plus the dimension of the image. So there are several consequences to this theorem. Many times we have the notation n for the dimension of the first space and m for the dimension of the V space, especially when we work with matrices. We will talk about this in more detail in the next section. All these supposed to be non-negative numbers. We used the notation before. For the dimension of the null space, k was used. For the dimension of the image, we used the letter r. So then what we have is, well, the theorem said, theorem 4.2.2, that n equals to k plus r. We also have that the image of the transformation is a subspace of V. It could be equal to it. So with our notation, what this means is that r is less than or equal to m. Equality means that it's the same. So if r equals to m, then the image of t covers the whole V. That means t is surjective. So looking at this equation, n equals to k plus r, what we have from here, all of these should be again non-negative. So that means that r is less than or equal to n. Or more precisely, r equals to n minus k, and this is less than or equal to n. Then if n is less than m, which means the dimension of u is less than the dimension of v, then what we have is that r less than or equal to n less than m, that is the dimension of the image is less than, strictly less than, the dimension of the V space, which says that t is not surjective. It says that t is not surjective. If, on the other hand, we have n larger than m, which means the dimension of u is larger than the dimension of v, then we have that k, which can be written as n minus r, is less than n minus m, since this is always true that r is less than or equal to m, and this inequality is maybe non-strict inequality. But then if n is less than m, then we have that this is positive, which means the dimension of the null space is positive, and that implies that several vectors might have the same zero image. So the transformation T is not injective, which means not one-to-one. So we have several special cases to see when a transformation is surjective and when it's not surjective or not injective. So in the first step, in the next section, we will use it for matrices. There is also a small definition here that the dimension of the null space is also called the nullity of T. Section 4.3 is rank and nullity applied to matrices. Capital M subscript mn of F denotes the m by n matrices over the scalar field F. This is in fact vector space, but right now we're not going to work with that specifically. We introduced before for a matrix that was m by n. Well, we will use mostly real numbers for the scalar field, but at some point actually we will also use complex numbers. Let's concentrate right now on real numbers for a while. So we considered before this linear transformation. This is actually a linear transformation between Fn and Fm. And the definition of this is that you apply to an n vector by multiplying the vector with a matrix from the left. So it's left multiplication by A. Since matrix vector multiplication is not commutative, sometimes we even use right multiplication. So there is a so-called rank of a matrix. It has several possible ways of defining it. The notation is rank of A, and this is the dimension of the row space. And it turns out that this is the same as the dimension of the column space. Here, the row space of A is the vector space spanned by the rows of A. And similarly, the column space is the vector space spanned by the columns of A. In fact, the easiest way to calculate this rank is to calculate the reduced row echelon form of A using, for example, Gauss-Jordan elimination, and then the number of pivot entries equals to the rank of A. The right null space of A is the set of all x vectors from Fn such that Ax equals to 0. So it's called right null space because A is multiplied by the x vector from the right. This is the same as the null space of this T transformation. Then when we multiply this matrix with the vector x from the right, one way to write this, if A matrix has columns A1, An, then x must have entries x1, xn. What this gives us is a linear combination of the column vectors. So this will be actually an element of the image of the TA transformation. And this is actually the same as the column space of A, since this is the linear combination of the columns of A. And then using our notation for the rank, that means that according to the definition and the previous theorem, what we have is that n, the dimension of U, which is in our case the Fn space, is the dimension of the null space of TA plus the dimension of the image of TA. That was the previous theorem. And using it for our special case with the matrix, the null space is actually the right null space of the matrix A, and the dimension of the image is the dimension of the column space, which is the same as rank of A. Although we don't often use this, it's also possible to get the equation for the Fn space. Then what we get is the dimension using the left null space of A plus the rank of A. It would be the rank or the dimension of the row space, but it's the same as the column space dimension. I will state this next theorem without proving it. It's a very nice calculation with matrix sizes. So let A be a m by n matrix, and then we have over, let's say, the scalars F, and B n by P matrix. The notation is n comma P over the same scalars F. Then we have the following arithmetic. The dimension of the right null space of AB. So notice that A and B can be multiplied together because these dimensions match. And then what we get is actually AB will be a matrix which is m by P. And then what we have is that the dimension of the right null space of this AB product is less than or equal to the dimension of the right null space of A plus the dimension of the right null space of B. The second property is that the rank of A plus the rank of B minus the rank of A times B is less than or equal to n. And just to explain what's going on without going through the whole proof. So first of all, B is a multiplication that goes from P into N. So this is Fp and this is Fn. And if you have an x vector, then Bx will be in Fn. And then once you are there, then you can apply A to it to get ABx, which is the same as AB times x. And then this is in Fm. So what we get is that this AB multiplication actually goes from P to M dimensions. So what we have is we have a null space of A here somewhere. It has some dimension. But since we start with B, we actually get, as a combination of the two maps, we might get a smaller null space than the sum of the separate null spaces. Since some of the entries already go to 0 when we multiply with b, those stay 0, and then we might have some additional vectors that also go to 0 under a.